Now, we know about context-free grammar, how to identify ambiguous, also how to identify unambiguous, but we do not know the algorithm to check ambiguous and unambiguous, because there is no generalized algorithm to check the ambiguous and unambiguous. That is the reason we need to practice many examples that we have seen in the previous session, how to identify the ambiguous and unambiguous CFG. Now, we are going to understand what is the language generated by the given CFG. In the previous sessions, we also seen about regular grammars. When I have given a regular grammar, we tried what is the language generated by the given regular grammar. The same way, we are going to practice the language generated by the context-free grammar. The first question, it is a simple grammar that we know how to understand the grammar when we have a left and right recursion. So, let me talk about the first left recursion. How do we understand the grammar which has left recursion? When the grammar which has left recursion, the AA term is going to be repeated and the non-recursive, that non-left recursive term is going to be placed at the end. Right? If you want to derive this string, then AA is going to be repeated any number of times. If you want to stop this recursion with S, then B has to appear in place of S. So, what is the language that is generated from this grammar? That is AA star and S always there before AA, so that S has to be replaced with B at the end. So, language should be B followed by any number of AAs. So, this is, look at the minimum string is B, and next minimum is going to be BAA, and next minimum is going to be SAA, replace S with again SAA. So, 4 S comes here, and to stop the S we need to replace with B. So, this is the language generated by the given context-free grammar, and we know that any language that is generated by the context-free grammar is going to be a context-free language. So, this is the context-free language, and also you know this is the regular language. Every regular language is a context-free language. Every regular language is a context-free language, because all the regular languages are there inside the context-free languages. Now, the grammar, whether it is regular grammar or not, still it is possible to generate a regular language, right? So, context-free grammars have no restrictions in the RHS side, so it can generate regular, it can generate some of the non-regulars. So, this is already regular grammar, so definitely generates regular language. Second one, S2 AA S or B. It is the right recursive grammar. Concept is same again. The recursive term has AA, and that AA is going to be repeated as many times we want, and S has to be stopped when we replace S with B. Now, what is the language by this second grammar? That is AA whole star, but the recursion stops with S when you replace with B. So, that B should come after AA, and this is the language generated by the second grammar. Now, let us focus on some other grammar where the recursion is something different from left and right. That is, suppose S comes in between A and B. Then how do we understand this grammar? When you try to understand the language, think about first the strings, because a new kind of recursion, then we need to focus on the strings to understand the recursion. What happens? The strings that are generated from this grammar, minimum C you can generate, because S2 C directly available. Then ASB, you can replace S with C. So, next string is ACB. How do you get that? First take ASB, this S you replace with S. What is another way? First A, B, and S is there in center. This S you substitute with again ASB, then A, B, that middle S you can replace with C. What you understood from this? If you try to understand this grammar, the language generated is C definitely there, because to stop the recursion C has to be placed in center, but this A and B, this both will be repeated equal number of times. If one A comes, then one B definitely comes. If there are two A's before C, then two B's after C. So what do you understand from this form? A power n, B power n, such that n greater than or equal to 0. The first term n is equal 0, second term n is equal 1, third term is third string is going to be n is equal 2, and so on. So this is the language generated by the third one. So how do you understand this recursion? If S is there somewhere in the middle, the before S, after S, the number of times is going to be same. That is A power n, B power n will have a relation here, and C is going to stop the recursion with S. Now let us focus on the similar kind of recursion. We have not seen this kind of recursion in the regular languages, because the regular grammar we cannot use the non-terminal in between the production. You can use at rightmost or leftmost, but you can't use in the somewhere other than the left or right. Next, suppose you have A, S, B or epsilon, then the concept is same. The A and B is going to be repeated, no doubt, but how many times it's going to be repeated? Equal number of times. So you have to write A power n, B power n. The recursion stopped by epsilon, so you have to put epsilon in center. It's nothing but just A power n, B power n, and n is definitely here. The minimum value is greater than or equal to 0. Right? This could be easy if you can understand the type of recursion that we are dealing here. Is it clear? Next one. Suppose I have double A, S, B or epsilon. Now focus similarly how the recursion is going to be. In previous grammar, the recursion is there in the center, and before A, after B, that is going to have a same number of times. Now before S we have a double A, after S we have a B. So double A treat as some term like X, then X power n, nothing but double A power n. So how do you deal that now? Double A assume as a one term before S, then these two terms are going to have same count. Then how do you write that? Double A power n, B power n, the recursion is going to stop when you substitute epsilon in place of S. This is nothing but double A power n, B power n. You can also write the double A as A power 2. So you can write that A power 2 is going to be there n times, nothing but A power 2n, B power n, where n is greater than or equal to 0. This is the fifth grammar that we have understood. Now let us focus on next grammar. Now sixth one, S2. Now I am going to use similar kind of grammar, that is double A, S, double B, and this could be easy for you now. You understood how to do that. Directly I am going to write the language for this. Before S double A, after S double B, so A power, that is double A power n and double B power n, in center epsilon is there, no need to write, because language is going to be double A power n, same as A power 2n, B power 2n, where n is greater than or equal to 0, right. Now let us practice one more grammar. Now let me write S2 A B, and where A is AAB or epsilon, capital B is CB or epsilon. Now how do you focus about this grammar? When you have more non-terminals, look at which non-terminal is easy to generate the strings. If you think about capital B especially, B can generate only C's, and that is very easy to understand in the beginning. So first focus on B, and also you can focus on A simultaneously, because A depends on A only, B depends on B, so you can write them easily. When you want to think about S, A and B already understood, so S can be easy to derive. Now what is the language of B that generates from this grammar? If I ask what is the language generated by B, you can say C star. How do you do that? The C is going to be recursive term, the epsilon is going to be placed here. So C star followed by epsilon, nothing but C star. And this A to AAB or epsilon is same as a fourth grammar, that is ASB or epsilon, where S is a non-terminal, here S is a non-terminal. So what is the language of A? It is A power n, B power n, A power n, B power n, and that epsilon when you place in center, you no need to write that, right? So A power n, B power n. Finally the language generated by the whole grammar, that is S is going to represent. S nothing but the language generated by the grammar, because S depends on A and B. A and B we know now. So what is the language that you get? A followed by B, that means language of A followed by language of B. So now write the language of A is A power n, B power n, and what is the B language? Is a C star. And you can represent many ways, that is A power m, B power n, C power k, such that, and you know A and B should be equal, A's and B's, so m is equal to n, and all of them are greater than or equal to 0. So you can add one more condition, m comma n greater than or equal to 0. So this is how we represent the language. Now let me write one more grammar. So can you think about this one? S2 AB looks like similar A2 AAB or epsilon, B2 BB or epsilon. So small change in the grammar. Instead of C's, I am putting the B's generated by the capital B. Here the B generates B star, and this generates A power n, B power n. Now when you come to the language generated by the grammar, the capital A is A power n, B power n, and capital B is B star. So what do you get here? That more B's you can generate when you compare with A's. So this, what do you write in place of A power n, B power n? B star. So I am writing here A power n, B power n, B star, nothing but A power m, B power n, such that m less than or equal to n, where m comma n greater than or equal to 0, because more B's you can generate when you compare with A because of the B star. So the number of B's is greater than or equal to number of A's, or you can say number of A's is less than number of B's. So we have understood some of the languages, how do you generate from the given context free grammar. And when you write a context free grammar, the language may be regular or non-regular, it generates, but definitely generates a context free language. Every context free grammar generates context free language, but some of the context free languages are regular, some of them are non-regular.